Gary. Good. Gary heard me in the back. That means I don't need a microphone. Okay, this is the final session of the conference. I'm going to face myself here. The first talk, the first talk of the session is characterizing phonon interactions in single molecules for non-classical light sources. So it's a sort of vaguely sources-oriented session, and Chloe is the first talking about molecules.
Yes. Hello everybody, so thank you for that introduction. So yes, this is a talk based on the poster that I presented yesterday. So I'm going to jump straight into the motivation of my research. And in recent years, single organic molecules have gained attention as novel non-classical light sources. So an example of one of these molecules is Bqit, and that has been found to emit single photons deterministically, and it also hosts a range of other attractive properties that are useful for quantum information applications. So some of these properties include a lifetime limited zero phonon line spectral width, and here is one of these log scale spectras, and this is the zero phonon line. We also have a high emission into the zero phonon line at around 40%. And finally, these molecules can be tuned, and they're also photostable. So collaborators at Imperial College London, in the group of the Centre for Cold Matter, which is led by Ed Hines and Alex Clark, have developed an efficient way to grow thin crystals of anthracene doped with this Bqit molecule. And you can see here's a microscope image of the anthracene and these red dots of the Bqit molecule. So the aim of my research is to model the dynamics of this Bqit anthracene environment and try and characterize the phonon interactions that are at play. So now going into the model, so I've come up with an open quantum systems model to go about this problem. And what we can do is split the Hamiltonian into three parts, where the first part is the system, and that contains a two-level electronic system of the Bqit molecule itself in its ground and excited state, and emission from the excited to the ground state corresponds to this zero phonon line. We also have in the system a discrete number of local vibrational modes, and these are also from the Bqit molecule itself, and these appear in the spectrum in the form of these side peaks. So the next ingredient for the Hamiltonian is the environment. So firstly, we have the electromagnetic environment that is included such that you can calculate spectra. And then we have a residual phonon bath. Now this bath is from the anthracene crystal environment, and it's coupled separately to the local vibrational modes and also coupled to the two-level system, where it's important to note that the second residual phonon bath, the electron-phonon interaction has been derived to second order to try and capture some of the pure dephasing effects that occurs on this zero phonon line. The final ingredient is the interaction terms, and that just contains the terms that connect all of the objects together. Finally, I want to note that we've got some arrows appearing in this model, and this is modeling the feedback between the relevant objects. This feedback is captured by the means of a Polaronframe transformation. So what is the Polaronframe? Well, in the quantum dot community, it's used frequently between the two-level system and a phonon bath. And what effectively it means is moving into a basis such that in the excited state, you account for the distortion of the lattice that occurs when your electron is excited. So this has been implemented for the molecule between the anthracene bath and the two-level system. And what's quite novel about this model is I've done a second Polaron transformation, but this time between the two-level system and the local vibrational modes, where the motivation for this is so that you move into a basis such that there's no longer any system terms that are interacting, and that makes the derivation of the master equation easier to handle. So now we have a Polaronframe Hamiltonian. I've then derived a Born-Markov master equation in this Polaronframe, where what that means is if you move back into the standard basis picture, you actually have a non-Markovian master equation. So what you can see here is the commutator of these local vibrational modes and 4 dissipator terms that will be described when I show you what I've plotted from this master equation. So the first thing I've done is now derive a spectral function, so we can look at some of the results. So here we have 4 spectral emission plots of the DBT Anthracene system at 4 different temperatures, where the grey line corresponds to the experimental data collected by the collaborators at Imperial College, and the red dashed line is the model. So one of the first things I want to pick out is this 0 phonon line. Now this occurs at 0 inverse picoseconds, excuse the units, but what that corresponds to is at around 784 nanometers, so it's near infrared range, and that corresponds to this transition from the excited to ground state. We next have these side peaks, and these correspond to the local vibrational modes that have been included into the system Hamiltonian. And you can see here that I've included 3 separate ones, and the reason for this is that as they're modeled as harmonic oscillators, you'd expect them to be equally spaced from the 0 phonon line if they were from the same mode. So the next feature that I want to describe out of these emission plots is the dephasing that was present in the master equation dissipators. So firstly, we have this gamma 1, which is a spontaneous decay rate of the DBT molecule. And this corresponds to around a lifetime of about 4 nanoseconds. And what this implements is a finite broadening to the 0 phonon line. We then have the dissipators small gamma, which is a temperature-dependent pure dephasing rate. And this dephases the 2-level system. And finally, we have kappa, which corresponds to a dephasing rate that applies to the local vibrational modes. The phonon spectral bath that has been used to calculate kappa and small gamma is in the following form. So the next thing to mention when describing this spectra is the sideband that you can see on each of these peaks. So to show this more clearly, I've plotted the sideband and the 0 phonon line local vibrational contributions separately, where this sideband has come from the fact that you've done a Polaron transformation between the 2-level system and the residual phonon bath. Because what this does is it includes information regarding the continuum of the anthracene crystal into the system, such that you're explicitly calculating radiative transitions from the excited state down into the continuum, and then from the continuum into the ground state. What's interesting about this model is that because you've got these local vibrational modes included into the system, you have a sideband on all spectral features. So the next results that I want to kind of delve a bit deeper into is looking at the 0 phonon line. So this is the 0 phonon line for 4 different temperatures on a log scale, so you can clearly see how the model is fitting the data. Now, what's important to note here is that this rate, this pure dephasing rate that I mentioned that was derived, captures the broadening quite well, and this has come from the second-order coupling of the 2-level system phonon-bath electron-phonon interaction. So finally, some of the calculations I've done that I displayed yesterday is a filter calculation, and this is just the spectral function with a Lorentzian filter applied to it, and you can see as the filter width decreases, these vibrational peaks kind of die off, and the sideband is suppressed. So that leads me on to my conclusion of the talk today. So we started off with a problem of trying to theoretically model this DBT single photon emitter, and we did that by a quantum open systems model. And this has led to capturing some things such as the 0 phonon line, these local vibrational modes, the relevant dephasing of the system, and finally this sideband that seems to be attached to all spectral features. The future work that I plan to do is to calculate some indistinguishabilities with some of the filter calculations, and also implement a cavity into the model. And the collaborators at Imperial, you can see they've already starting to work on implementing a microcavity with these DBT molecules. So finally, I just want to say some acknowledgements to some collaborators, Alex Clark and Ross, who are at Imperial College London, and they've supplied all of the data that I've shown today in this talk. Also, I want to acknowledge Jake R. Smith's work. He's been a really good hand with some of the theory. And finally, my supervisor, Dara McCutcheon. So thank you very much for your attention.
So the paper is in questions. I should add that this was upgraded from a poster to a short presentation. One of the couple of things that we've upgraded from poster to.
Would the spectrum of the phonons of the host change substantially if you went down to just a few layers of the 2D host material?
Yeah, so this particular data is from a nanocrystalline itself. So these crystals are already quite thin. Like we mentioned yesterday, they're about 100 layers thick of the anthracene. And because this system is layered, I can't imagine that the bath coming from a separate layer bonded by van der Waals would have a really strong effect on the dephasing, as you can kind of imagine these things being dephased in plane. So I'd be surprised if it suppressed that much by kind of reducing off the layers. However, yeah, maybe if you went to if you scotch taped it and went to a really thin nanocrystal layer, it would be an interesting point to see, would the contribution of these vibrational modes decrease heavily? In the dephasing of the actual anthracene itself. But it's already quite thin because of the fact you've got van der Waals bonding between these crystals. So, yeah.
Any other questions at this stage? You may have already asked all your questions at the poster yesterday, which you all dutifully went and saw, I hope. But anyway, thank you very much, Chloe, and we'll move on to the next.